Thanks for watching, and here is a very elegant way to show that a PDE is linear. And so in particular, let's show that uxx plus x squared uyy equals e to the y is a linear PDE. And this has to do with linear transformations from linear algebra. So let me remind you, a function or a transformation L is linear if two things hold. First of all, L of u plus v is L of u plus L of v for all u and v, and L of a constant times u, so LCu is CL of u for all u and constant c. In other words, you can just take the c out in this case. And then what is the definition of a linear PDE in that case? A linear PDE is a PDE of the form L of u is f, where L is a linear transformation. L is linear. That is, L satisfies those two properties. And well, let's use that to show that this PDE is linear now. So once again, we have our PDE, uxx plus x squared uyy equals e to the y. Notice, this is of the form Lu equals f, where L of u is uxx plus x squared uyy, and e of y is the inhomogeneous term f. So really, all this boils down to is to show that L is linear. So let L of u be uxx plus x squared uyy, and then show L is linear. Because then we're done. Then it's of the form Lu equals f, where L is linear, and then the PDE becomes linear. Okay, so to show that L is linear, we just need to calculate L of u plus v. It's almost like I love you, but in linear algebra. So that becomes u plus v xx plus x squared u plus v yy. And then you can expand out the derivatives, again, because differentiation is linear. And then plus x squared uyy plus v yy, and then just group like terms. So we have uxx plus x squared uyy plus vxx plus x squared vyy, and that's precisely L of u plus L of u. So already additivity is true, and then let's do the same thing for scalar multiplication. So in this case, L of cu, that becomes cuxx plus x squared cuyy. And once again, we can pull out the constants out of the derivative. So cuxx plus x squared cuyy. And now we can pull out c from this equation. So it's cuxx plus x squared uyy. But that's precisely CLU. And therefore, once again, L is linear, so we have a PDE of the form Lu equals f, where L is linear, and therefore the PDE is linear by definition. Now, you may ask, Why is this so important? I mean, it's kind of obvious that it's linear because they're just derivatives here and functions of x and y. Well, it's more important in theoretical purposes. In fact, I want to show you a quick application of this. And in fact, let's show the following neat fact. Namely, for linear homogeneous PDE, what does linear homogeneous mean? It means of the form LU equals 0. So once again, linear means L is a linear transformation, 0 means homogeneous. Let's show that the sum of two solutions is still a solution. In other words, if you have two solutions of that PDE and you add them up, then the sum is still a solution of that, which is very neat. So why? Well, suppose U and V are two solutions. So what does that mean? It means LU equals 0 and LV equals 0. By definition of our PDE, then if you take U plus V, so consider U plus V, and let's check if this is a solution. Well then, what do we know? Well, LU plus V, that is LU plus LV, but we know LU is 0, LV is 0, so this is 0. So what does that tell us? It tells us that LU plus V is 0. So in other words, U plus V satisfies our PDE, and all this means is that U plus V is a solution. And you see, the point is, this works for any linear homogeneous PDE. That's why, even though it's a little bit more abstract, it's also more elegant for showing such kind of theoretical results. All right, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.